All right, in this explainer, we're going to walk through the essential process of designing slender reinforced concrete columns. Think of me as a senior engineer, and I'm walking you through the code, the calculations, and just as importantly, the why behind it all. Let's get right into it.
So here's our game plan. We'll kick things off with why this is even a big deal. Then we'll get our key terms straight. That's super important. After that, we dive into the calculations, including that tricky K factor. We'll work through a real example to make it all click, and then wrap up with a handy checklist. The goal here is to get you super confident with this whole procedure.
First things first, let's set the stage. What is the fundamental problem we're trying to solve here? I mean, why do we have a whole separate procedure for slender columns anyway? What's really going on?
And boom, this side-by-side just nails the issue, doesn't it? A short, beefy column. It barely moves under load. But a slender column, like you see in image A, it actually bends. And that deflection creates a whole new problem, a secondary moment. We call it the P delta effect, because you have the axial load, P, acting on that deflection, delta. And that secondary force, it's dangerous, and we absolutely have to account for it in our design.
Okay, so with that in mind, let's dig into how the code formally defines these columns and, why these rules exist in the first place. It's all about keeping our buildings safe.
So, here they are. These are the magic numbers from the code, your official thresholds. It's a pretty simple ratio, effective length divided by the column's dimension. If that number is bigger than 15 for a braced column or 10 for an unbraced one, well, welcome to slender column territory. You've got to follow the procedure.
And here's the crucial why. All of these rules, all these extra steps, are here to make sure that if a failure were to ever happen, it's a predictable one. We want a failure that happens because the steel yields, which gives you a warning, not a sudden catastrophic buckling failure where the column just snaps. It's all about ensuring a safer, more ductile behavior.
All right, now for a really critical distinction that's going to affect every single calculation we do from here on out. Is the column in a braced system or an unbraced one? This is one of the very first calls you have to make.
This breaks it down perfectly. In a braced structure, you've got these dedicated, super stiff elements like shear walls that do all the heavy lifting when the wind blows. But in an unbraced structure, the whole frame has to work together, the columns and beams bending to resist those same lateral forces.
This plan view makes it crystal clear. Look at the left in A, no shear walls, right? That's a classic unbraced frame. But then look at B. See those thick black lines? By adding those shear walls, we've now braced the structure. But notice, it's only in the X direction. It's still unbraced in the Y direction. That's a really key detail to catch.
And this just builds on that last idea. Here you can see fully braced systems. You can use shear walls on both axes, like in C, or you can use a stiff central core, like around an elevator shaft in D, to brace the entire building in every direction.
In this slide, this is the payoff. This shows you the consequence of that braced versus unbraced decision. In a braced column, the ends are basically held in place, so that extra moment from bending happens right near the middle. But in an unbraced column, the whole thing sways, and that maximum moment gets pushed to the end of the column. This is absolutely critical for our calculations.
Okay, with that background, let's get into the fun part, the numbers. We're going to break down the different moments that we have to combine to get our final design moment. It's not just one thing. It's a recipe of different effects.
This visual is awesome because it just lays it all out. Diagram B is your initial moment, the one you get from your regular structural analysis. Diagram C, that's the sneaky one, the extra moment caused by the P delta effect. And our final design moment in D is just adding those two together. Simple as that.
So these are the three main players we need to figure out. You've got your initial moment from the analysis, then a minimum moment to account for the fact that nothing's built perfectly straight in the real world, and of course, that all-important additional moment that comes from the column being slender. And here's something else you have to watch out for, the bending shape. Sometimes a column bends in a simple C shape, but here you see it bending in an S shape. We call that double curvature. When that happens, you have to treat the smaller end moment, M1, as a negative number when you're calculating your initial moment, MI. Don't forget that.
Okay, deep breath. This next part, the K factor. This is where a lot of new engineers get a little bit tangled up, but it's just a critical refinement step. So let's demystify it together.
So what is this K factor? Well, it basically corrects our calculation for how the axial load affects the column's stiffness. But here's the tricky part.
The value of K depends on the final amount of rebar in the column, which we don't know yet because we haven't designed it. See the problem? It's kind of a chicken and egg situation. So the way we solve it is to start with a smart guess and then check our work.
So here's the game plan. You always start by just assuming K is 1.0. Easy enough, right? Then you run through the whole design based on that assumption. You pick some rebar, and then you calculate what K should have been with that rebar. If your new calculated K is pretty close to the 1.0 you started with, perfect, you're done. If not, no big deal. You just take that new K value and run the calculation again. You just repeat until your assumed value and your calculated value basically match.
All right, enough theory. Talk is cheap, right? Let's get our hands dirty and see how all of these steps come together in a practical, real-world calculation for an unbraced column.
First up, we check our slenderness ratios. Now for an unbraced column, remember our limit is 10. And what do we see? About the strong XX axis, the ratio is 9.6. That's less than 10, so it's short in that direction. But look at the weaker YY axis. The ratio is 14.3. And boom, that's over our limit. So it's official. This is a slender column, and we have to do the full design procedure. Okay, next we crunch the numbers for our moments. Our initial moment, me, comes out to 108 kilonewton meters. Then we calculate the additional moment, mad D, and for our first attempt, we assume K equals 1. That gives us 100. The code tells us to check a few different combinations, but our controlling value here is adding the initial and the additional moments together, giving us a final design moment of 208.
And here's the punchline. Our final design moment is 208 kilonewton meters. Now think about that. The biggest moment that was actually applied to the column was only 120. That slenderness effect has added a massive amount to the force we need to design for. This is exactly why you can never, ever ignore it. Okay, let's bring it all home. We're going to consolidate everything we just talked about into a single, clear procedure that you can use on your own projects to make sure you don't miss a step.
Think of this flowchart as your best friend for this process. It's your roadmap. It literally walks you through every single decision. You start at the top. Is my structure braced or unbraced? Okay, it's unbraced. Next question. Is the slenderness ratio greater than 10? If no, you go down the easy short column path. If yes, you follow the long column path, which includes calculating that additional moment and everything we just worked through. The entire process is right here on one page.
So look, we've given you the tools to correctly design a slender column, which is great. But the final thought I want to leave you with is a bit bigger. Now that you understand these secondary moments, how might that change the way you think at the very beginning of a project? Maybe making a column a little bit bigger or adding a shear wall strategically can help you control these effects before they even become a problem. It's about shifting from just calculating to truly designing.